In abstract algebra, the concept of a module over a ring is a generalization of the notion of vector space over a field, wherein the corresponding scalars are the elements of an arbitrary given ring and a multiplication is defined between elements of the ring and elements of the module. Thus, a module, like a vector space, is an additive abelian group. A product is defined between elements of the ring and elements of the module that is distributive over the addition operation of each parameter and is compatible with the ring multiplication. Modules are very closely related to the representation theory of groups. They are also one of the central notions of commutative algebra and homological algebra, and are used widely in algebraic geometry and algebraic topology. Introduction. Motivation equals. In a vector space, the set of scalars forms a field and acts on the vectors by scalar multiplication, subject to certain axioms such as the distributive law. In a module, the scalars need only be a ring, so the module concept represents a significant generalization. In commutative algebra, both ideals and quotient rings are modules, so that many arguments about ideals or quotient rings can be combined into a single argument about modules. In non-commutative algebra, the distinction between left ideals, and modules becomes more pronounced, though some ring-theoretic conditions can be expressed either about left ideals or left modules. Much of the theory of modules consists of extending as many as possible of the desirable properties of vector spaces to the realm of modules over a well-behaved ring, such as a principal ideal domain. However, modules can be quite a bit more complicated than vector spaces. For instance, not all modules have a basis, and even those that do, free modules, need not have a unique rank if the underlying ring does not satisfy the invariant basis number condition, unlike vector spaces, which always have a basis whose cardinality is then unique. Formal definition equals, suppose that R is a ring and 1 R is its multiplicative identity. A left-A module M consists of an abelian group and an operation R, M such that for all R, S in R and X, Y in M, we have. The operation of the ring on M is called scalar multiplication, and is usually written by juxtaposition, that is as Rx for R in R and X in M, though here it is denoted as Rax to distinguish it from the ring multiplication operation, denoted here by juxtaposition. The notation Rm indicates a left-A module M, a right-A module M, or Mr. is defined similarly, except that the ring acts on the right. That is, scalar multiplication takes the form M, R and M, and the above axioms are written with scalars A and S on the right of X and Y. Authors who do not require rings to be unital omit condition 4 above in the definition of inner module, and so would call the structures defined above unital left-A modules. In this article, consistent with the glossary of ring theory, all rings and modules are assumed to be unital. If one writes the scalar action as Fr so that Fr, X, equals Rax, and F for the map that takes each R to its corresponding map Fr, then the first axiom states that every Fr is a group homomorphism of M, and the other three axioms assert that the map F, R and M, given by Rafr is a ring homomorphism from R to the endomorphism ring end, M. Thus a module is a ring action on an abelian group. In this sense, module theory generalizes representation theory, which deals with group actions on vector spaces, or equivalently group ring actions. A bimodule is a module that is a left module and a right module such that the two multiplications are compatible. If R is commutative, then left-R modules are the same as right-R modules and are simply called R modules. Examples: if K is a field, then the concepts K vector space and K module are identical. If K is a field, and K, X, a univariate polynomial ring, then a K, X, module M is a K module with an additional action of X on M that commutes with the action of K on M. In other words, a K, X, module is a K vector space M combined with a linear map from M to M. Applying the structure theorem for finitely generated modules over a principal ideal domain to this example shows the existence of the rational and Jordan canonical forms. The concept of a Z module agrees with the notion of an abelian group. That is, every abelian group is a module over the ring of integer Z in a unique way. For n greater than 0, let NAX equals X plus X, 0 AX equals 0, and AX equals A, NAX. Such a module need not have a Bezier groups containing torsion elements do not. The decimal fractions form a module over the integers. Only singletons are linearly independent sets, but there is no singleton that can serve as a basis, so the module has no basis and no rank. If R is any ring and N a natural number, then the Cartesian product Rn is both a left and a right module over O if we use the component-wise operations. Hence when n equals 1, R is in a module, where the scalar multiplication is just ring multiplication. The case n equals 0 yields the trivial a module 0 consisting only of its identity element. Modules of this type are called free, and if A has invariant basis number, the number n is then the rank of the free module. If S is a non-empty set, M is a left R module, and MIS is the collection of all functions f, S and M, then with addition and scalar multiplication in MIS defined by S equals F, S, plus G, S, and S equals RF, S, MIS is a left R module. The right R module case is analogous. In particular, if R is commutative, then the collection of a module homomorphisms H, M and N is in a module. If X is a smooth manifold, then the smooth functions from X to the real numbers form a ring car, X. The set of all smooth vector fields defined on X form a module over car, X, and so do the tensor fields and the differential forms on X. More generally, the sections of any vector bundle form a projective module over car, X, and by Swann's theorem, every projective module is isomorphic to the module of sections of some bundle. The category of car, X, modules and the category of vector bundles over X are equivalent. The square n by n matrices with real entries form a ring R, and the Euclidean space Rn is a left module over this ring if we define the module operation via matrix multiplication. If R is any ring and I is any left ideal in R, then I is a left module over R. Analogously, of course, right ideals are right modules. If R is a ring, we can define the ring ROP, which is the same underlying set and the same addition operation, but the opposite multiplication. If AB equals C in R, then bar equals C in ROP. Any left A module M can then be seen to be a right module over ROP, and any right module over R can be considered a left module over ROP. There are modules of a Lie algebra as well. Submodules and homomorphisms. Suppose M is a left A module and N is a subgroup of M. Then N is a submodule if, for any N in N and any R in R, the product RAN is in N. The set of submodules of a given module M, together with the two binary operations plus and a copyright, forms a lattice which satisfies the modular law, given submodules U, N1, N2 of M such that N1-N2, then the following two submodules are equal, a copyright N2 equals N1 plus. If M and N are left R modules, then a map F, M and N is a homomorphism of a modules if, for any M, N in M and R, S in R. This, like any homomorphism of mathematical objects, is just a mapping which preserves the structure of the objects. Another name for a homomorphism of modules over R is in a linear map. A bijective module homomorphism is an isomorphism of modules, and the two modules are called isomorphic. Two isomorphic modules are identical for all practical purposes, differing solely in the notation for their elements. The kernel of a module homomorphism F, M and N is the submodule of M consisting of all elements that are sent to 0 by F. The isomorphism theorems familiar from groups and vector spaces are also valid for R modules. The left R modules, together with their module homomorphisms, form a category, written as a mod. This is an abelian category. Types of modules, finitely generated. A module M is finitely generated if there exist finitely many elements x1, xn in M such that every element of M is a linear combination of those elements with coefficients from the ring R, cyclic. A module is called a cyclic module if it is generated by one element. Free. A free R module is a module that has a basis, or equivalently, one that is isomorphic to a direct sum of copies of the ring R. These are the modules that behave very much like vector spaces. Projective. Projective modules are direct summands of free modules and share many of their desirable properties. Injective. Injective modules are defined duly to projective modules. Flat. A module is called flat if taking the tensor product of it with any exact sequence of the modules preserves exactness. Torsionless module. A module is called torsionless if it embeds into its algebraic dual. Simple. A simple module S is a module that is not zero and whose only submodules are 0 and S. Simple modules are sometimes called irreducible. Semisimple. A semisimple module is a direct sum of simple modules. Historically, these modules are also called completely reducible. Indecomposable. An indecomposable module is a non-zero module that cannot be written as a direct sum of two non-zero submodules. Every simple module is indecomposable, but there are indecomposable modules which are not simple. Faithful. A faithful module M is one where the action of each RA perm L0 in or on M is non-trivial. Equivalently, the annihilator of M is the zero ideal. Torsion-free. A torsion-free module is a module over a ring such that 0 is the only element annihilated by a regular element of the ring. Noetherian. A Noetherian module is a module which satisfies the ascending chain condition on submodules, that is, every increasing chain of submodules becomes stationary after finitely many steps. Equivalently, every submodule is finitely generated. Artinian. An Artinian module is a module which satisfies the descending chain condition on submodules, that is, every decreasing chain of submodules becomes stationary after finitely many steps. Graded. A graded module is a module with a decomposition as a direct sum M equals AX MX over a graded ring R equals AX or X such that RX MX plus Y for all X and Y. Uniform. A uniform module is a module in which all pairs of non-zero submodules have non-zero intersection. Further notions. Equals relation to representation theory equals, if M is a left R module, then the action of an element R in R is defined to be the map M and M that sends each X to Rx, and is necessarily a group endomorphism of the abelian group. The set of all group endomorphisms of M is denoted NZ, M, and forms a ring under addition and composition, and sending a ring element R of R to its action actually defines a ring homomorphism from R to NZ, M. Such a ring homomorphism RNZ, M, is called a representation of R over the abelian group M. An alternative and equivalent way of defining left R modules is to say that a left R module is an abelian group M together with a representation of R over it. A representation is called faithful if and only if the map RNZ, M, is injective. In terms of modules, this means that if R is an element of A such that Rx equals 0 for all X in M, then R equals 0. Every abelian group is a faithful module over the integers or over some modular arithmetic Znz. Equals generalizations equals, any ring R can be viewed as a pre-additive category with a single object. With this understanding, a left R module is nothing but an additive functor from R to the category AB of abelian groups. Right R modules are contravariant additive functors. This suggests that, if C is any pre-additive category, a covariant additive functor from C to AB should be considered a generalized left module over C. These functors form a functor category C mod, which is the natural generalization of the module category R mod. Modules over commutative rings can be generalized in a different direction. Take a ringed space and consider the sheaves of OX modules. See sheaf of modules for more. These form a category OX mod, and play an important role in modern algebraic geometry. If X has only a single point, then this is a module category in the old sense over the commutative ring OX, X. One can also consider modules over a Samar ring. Modules over rings are abelian groups, but modules over Samar rings are only commutative monoids. Most applications of modules are still possible. In particular, for any Samar ring S, the matrices over S form a Samar ring over which the tuples of elements from S are a module. This allows a further generalization of the concept of vector space incorporating the Samar rings from theoretical computer science. Over near rings, one can consider near ring modules, a known abelian generalization of modules. See also, group ring, algebra, module spectrum. Notes. References, F. W. Anderson and K. R. Fuller, Rings and Categories of Modules, Graduate Texts in Mathematics, Volume 13, 2nd ed., Springer Verlag, New York, 1992, ISBN 0-387-97845-3, ISBN 3-540-97845-3, Nathan Jacobson. Structure of Rings. Colloquium Publications, Volume 37, 2nd ed., AMS Bookstore, 1964, ISBN 978-0-8218-1037-8. External links, Haswinkel, Michiel, ed., Module, Encyclopedia of Mathematics, Springer, ISBN 978-1-55608-010-4. Why is it a good idea to study the modules of a ring? On Math Overflow, module in ALll.